Welcome. This is the last lecture of module 3, where we will briefly discuss about the rank of a matrix and linear independence. Actually, both of these things maybe we will not directly use it, but it is better to know these things during this course, because it is the foundation of when you learn the advanced structural analysis like finite element method and other methods. One important thing is rank of a matrix. Rank of a matrix, all of you know probably that a matrix is invertible when its determinant is non-zero. So, we are talking about a square matrix where the determinant is possible. So, essentially what does this determinant shows is the singularity of the matrix. A matrix is essentially non-singular if it is determinant is non-zero. So, here we will extend this concept that determinant of a matrix or more effectively the rank of a matrix. So, essentially what I mean this extension is, if the matrix is rank deficient matrix, then its determinant is not possible and its determinant is obviously 0. So, that we can easily find out. For instance, if we see that there is an identity matrix, and then if we make suppose there is a identity matrix for which we know the determinant is 1. So, now if you encounter a matrix where one of the rows of the matrix is essentially 0, or you can make it 0 by row elimination or the echelon form that we have learned earlier. So, this matrix is essentially the determinant is essentially 0. So, that this matrix, even though this rank of this matrix is 3, but here the rank of this matrix is 2. So, I will define the rank soon. So, if the primary thing is, if there is a rank deficient matrix, then we cannot invert it, or it is a singular matrix. So, this concept will elaborate through first linear independence of vectors, and then we will define the rank of a matrix. So, let us see first what do I mean by linear independence. So, without any assumption or anything, let us consider a set of vectors v1, v2, v3 to vn. There are n number of vectors which is of dimension, say 2 dimension, 3 dimension, or n dimension or m dimension is possible. So, that means the components of vector could be any dimension. So, now let us write the combination of these vectors as follows and equate it to 0. For instance, I write this, that C1 V1, C2 V2, C3 V3, A and Cn Vn equals to 0. So, now here C1, C2, C3, C4 and Cn, these are the scalars, scalar quantity. So, what it means, for instance, if there is a vector 1 0 0, I multiply with the scalar say 1 or 2 or anything, -1, -2, something like that. Now, the definition of linear independence is, if these vectors are linearly independent to each other, if I have already explained what if means, that is if and only if all Ci's are 0, and then if I multiply these all constants, if I take all constants 0, and then obviously the right hand side has to be 0. So, That means there is no other possibilities of non-zero CIs such that the combination, this combination will make it 0. For instance, we will see through an example what this means. Let us see through an example. Consider the column of this matrix A. Now, this matrix has 3 columns. The columns are 1 0 0 3 1 0 4 3 minus 1. Now, as per our definition, I multiply C1 with this vector, C2 with the second vector, and C3 with the third vector, and equate it right hand side equals to 0. So, now I have to find out C1, C2, C3. Whether any possible values of C1, C2, C3 is either there or not, that is our goal. Now, see, if you look carefully, if you investigate carefully by looking at these equation, you see that C1, C2, C3 non-zero values are not possible, because suppose if I consider these two case, suppose now C2, if C2 is non-zero and C3 is non-zero, then certainly this quantity you cannot make it 0, equate 0 with the right hand side. I mean C2 is, if I take say 2 and C3 is, suppose I take 3 or 4, anything, any number, then C2 into 0 and 4 into minus 1, that is minus 4, which cannot be 0. So, similarly for C1, C2 and C3, you cannot make this quantity 0 or this quantity second equation 0 without having any non-zero, means without having C3, C2 and C1 is 0. So, so obviously C1, C2 and C3 has to be 0. For this case, otherwise this equation is not satisfied. So, that means there is no other possibility of non-zero CIs arises here. So, that is why we say these vectors are V1, V2 and V3. These vectors V1, V2, V3 are linearly independent vectors. So, these are linearly independent vectors. Now, consider another example where it is a rectangular matrix. So, now this matrix, if I consider the all columns of this matrix, now this is we can easily see that this row operation, if I do, that is R2 dash or R2 equals to R2 minus R1, then I can obtain the echelon form of this matrix or the upper triangular form of the matrix. So, you see in the previous example we have seen one important property, that this matrix, the upper this matrix is essentially upper triangular matrix. So, from where we can conclude one thing, that if there is a upper triangular matrix and if it is diagonal elements are non-zero, then we can easily say that the vectors, these column vectors of those matrix are essentially linearly independent vectors. Now, if we now look at the rectangular matrix, which is 1 0 2 1 and 1 1. So, what essentially we are doing? We need to solve essentially this into C1, C2, C3 to 0. So, this is that means we want to find out C1, C2 and C3. So, we have to solve these equations. So, how to solve these equations? Let us see. So, it is a rectangular equation. Naturally, these rectangular equations will have multiple solutions or indefinite amount of solution. We will see that. So, if I write it carefully now, the equations of this matrix, say C1. So, if I write it C1 plus C2, 2C2 plus C3, this has to be 0, and C2 plus C3 has to be 0. So, we have two equations, 3 unknowns. So, one of the variable I have to assume, then we can find out the other variables. So, here if you look carefully, these variables, if I solve it now, if I write it, So C2 or C3 is C2 is essentially minus C3. So now here C1 is essentially minus 2C2 minus C3. So essentially it is if I substitute C2, so it is minus C3. So essentially it is C3, right. So now here you see C1 and C2 I have represented in terms of C3. Now if I assume C3, there are different values for different C3s. So if I assume C3 is 1 suppose, and then I can now find out C1 equals to 1 and C1 equals to 1 and C2 equals to minus 1. So now here you have to understand very carefully that here I have assumed C3, then only these values are possible. So this variable essentially is known as free variable. That means that any possibilities or infinite number of values I can assume, and I can get infinite number of solutions. So you see going back to our linear definition of linear independence, that C2, C1, C2, C3 are non-zero possible. So if I write now that C1 into this vector, that is 1 0 plus C2 into this vector, that is 2 1 plus C3 into 1 1, I can produce this right hand side as 0 0, right, with these values. If I now write C3 equals to 1 and C1 equals to 1 and C2 equals to minus 1, I can produce a right hand side 0 0. So as per our definitions, so I can now say these vectors, that is V1, V2 and V3, they are linearly dependent vectors. So that means also we learn from one thing here, that this dependency is essentially due to this free variable C3, where all solutions C2, C1 are dependent on C3. So if I assume C3, I will get different values, I will get C1 and C2. If I assume different values of C3, I will get C1 and C2 different. So that means infinite number of solutions are possible, and so these variables are essentially known as the free variables, and these variables are essentially known as pivot variables. Probably you have heard this name earlier. So these variables are called pivot variables, C1 and C2. So now if I look carefully, or we will learn it, that this matrix is having rank 2. Why 2? Because there are 2 pivot variables. So if I write this matrix without the third column, of this matrix, then you will see that we cannot have C1 and C2 different here, means non-zero here, to produce right hand side 0. What I mean by this, that if I write these only 2 columns of this vector, that 2 columns of this matrix, that is 2 1, I cannot have a 0 0 unless C1 and C2 is essentially 0. But here in this case C1, C2 and C3 may be non-zero. Non-zero is possible. So here you see, if I remove the third column of this matrix, then it is the rank is 2, because all of them are pivot variable. Rank, I can say it is 2. Now I will define rank formally later. So what we have learned, among these C1 and C2 and C3, these are pivot variable. These are also pivot variable, these are also pivot variable, but this is known as free variable. So if there is a free number of free variable is, so this is a finally 2 cross 3 matrix. So there are 3 independent 3 unknowns. So among that, one of them is full free variable. So another 2 is pivot variable. So that is why the rank becomes 2. Now, let us now formally define what is essentially rank. So, suppose the elimination reduces Ax equals to B to Ux equals to C, and suppose there are R pivots and n minus R variables, R pivots are n minus R free variables, then the rank of the matrix A is R. So, essentially what I mean by this we will see through an example. Let us consider a simple example with a matrix. So, suppose I want to find out this equation, say 1 3 3 2 and then 2 6 9 7 minus 1 minus 3 3 and 4, and I have 4 unknowns. Suppose let us say A, B, C, D, right, 4 unknowns, and I have right hand side also, which is 1 5 5 5. So, this I am doing for a rectangular matrix vector equation, but all the rules are applicable for the square matrix. This if I have the square matrix, then we can connect it with the determinant of the matrix, but in case of a rectangular matrix we will not we cannot connect it for the determinant, and inverse is essentially right inverse and left inverse, all those things are there, but we are not required those concepts here. So, now if what we will do its echelon form, row reduced echelon form, or upper triangular form. So, I can just do this row operation that we have learned earlier. So, 1 3 3 2, let us make this thing same, and then I can just multiply 2 times with the first row with the and subtract it from the second row. So, it will be 0, then it will be 0, then it will be 9 minus 6, that is 3, then 7 minus 2 into 2 4, that is 3, and then this one in case of a third third row, I will just add the first row with the third row, then this will make 0 0, and then this will make 6, and this will make again 6. So, similarly I have to do it for the right hand side. So, now here this will becomes 1, and then 5 minus 2, that is 3, and then 5 plus 5 plus 1, that is 6. So, now again I can subtract it from the here. So, I will just write 1 3 3 2 0 0, then I can write it 3 3, and then 0 0, then 2 times of second row subtracted from the third row, it will be 0 0, and then this will be my A B C D, and then it will be my 1 3 and 0. So, now you see carefully this among these this matrix is now one row of this matrix is essentially 0. Now, if you look carefully, this row that means it is automatically satisfied, that means what this row 0 row means, that means 0 into A, 0 into B, 0 into A plus 0 into B plus 0 into C plus 0 into D will be 0. So, which is actually true. So, that means this equation has no meaning essentially. So, it is So that means here there is some free variable involved here. So we will see that what is that free variable. We can now do this more, means this operation I can do it more. I can actually divide by 3 by this second row and find out the reduced from 1 1 3 3 2, then 0 0 1 1 0 0 0 0, and then I can write it A B C D, and then I can write it 1 1 0. So now you see we can also go for pivots. That means here what will be the pivots. So as we know, we can make the entries just top of the pivot 0. So we can just simply do again subtract the first one. So we want to make this quantity, that is this one will be 0, because this will again a pivot element and this will also a pivot element. So we can make this thing 0 by just simply doing another row operation. So 1 3, then 3 times of second row minus first row, that is 0, and then because these quantities are 0, these quantities are 0, so it has no effect. So then again multiply 3 times with 1 and subtract 2 minus 3, so it will be minus 1, then again 0 0 1 1, then 0 0 0 0. So now here again I have to do the right hand side. So A B C D, and then right hand side will be 2 minus the simply minus 2. So because 3 times of 1 minus 3 is minus 2, and then 1, then equals to 0. So now you see, so final matrix, the row reduced echelon form is this. So here we can see carefully that only your this one is the pivot element and this one is pivot element. So top of that is also 0. So that means as per our rank definition, so there are r number of pivots. So here it is 2 number of pivots, and then what are those, and then naturally this matrix is 3 cross 4 matrix. So there are 4 variable. Among 4 variable, some variables are pivot variable, some variables are free variable. So which variables are free variable? If you look carefully, that these 2 columns actually has the corresponding variable of these 2 columns are actually free variable. So this we can also verify if we write in the equation form. So if I write it in a equation form, that is A plus 3B plus 0 into C plus minus 1 into D equals to minus 2. And the second equation will be C plus D equals to 1. So from here I can write C is actually 1 minus D, right. Now here A, from here I can write A equals to minus 2 minus 3B and then plus D. You see, so if I assume now D, and if I assume C, if I assume D, then I can find out C. what is the value of C. And here once I have assumed D, I have to also assume B, then I can get the value of A. So that means B and C are possibility are infinite. Possibility of B and C are infinite. So that means B and C are essentially B and D are essentially free variable, while A and C are essentially dependent variables. That means the pivot variable. If you look carefully, that in this matrix, the column 1 is essentially the pivot column, so it contains a pivot, and column 3 is also the contains the pivot element. So now here column 1 corresponds to variable A, and column 3 corresponds to variable C. So that means if we know the pivot elements belongs to which column, so we can also identify the which variables are pivot element, which variables are pivot variables. So A and C are essentially known as the pivot variable, and B and D are essentially known as the free variable. So you see in this matrix the number of variables is 4. So 4 minus let us summarize. So n is actually 4 here. So there are pivot variables, r is actually 2, and then free variables n minus r is actually 2. So that means rank of the matrix is 2. So we know how to calculate the rank of the matrix. So now see, for a square matrix, if it was a 4 cross 4 matrix, then rank has to be so suppose there is a square matrix. So let us see a square matrix. So the simple square matrix is identity matrix. So as I have discussed earlier, 1 0 0 0 0 1 0 0 0 0 1 0 and then 0 0 0 1. So now here this is a 4 cross 4 matrix. So that means here n is actually 4. Now this matrix is having how many variables? If I write the matrix vector equation, so say A, B, C, D, so 4 variables. So among these 4 variables, if n, that means here if you can see that if I write here A, B, C, D, all variables are actually pivot variables, because these are the pivot elements. These are the pivot element. So that means r here is actually 4. So n minus r, that means number of free variable, is actually 0. So when the rank is the for a square matrix, that means where the rank is essentially the number of the dimension of the matrix equals to the dimension of the matrix, we can invert that matrix, or we can solve the matrix vector equation uniquely. So that means since there is no pivot variable, that means there is no assumption required for the other variables to be found out. So the solution of the matrix vectors equation, that is Ax equals to b, will be unique. So that means if r equals to n, then we can invert the matrix, or we can have a non-singular matrix, or determinant is non-zero. So this is actually having a very important application in our case. So probably by this time you have learned what is actually the stiffness matrix of a truss, or stiffness matrix of a beam, stiffness matrix of a frame. So probably also we have deduced it, that is, if I have a truss element, so we will have the axial degrees of freedom only, and then the elemental, this is element E. So in the element we have first degrees of freedom and the second degrees of freedom corresponding to node 1 and node 2. So element stiffness matrix Ke we have found out from the unit load method or any method. So, which is we know that AE by L minus AE by L minus AE by L and AE by L. So, what is A? A is essentially the area of the member and E is the Young's modulus of the member. So, if I write it now, you see this KE is essentially KE is essentially your AE. If I take outside, then this becomes 1 minus 1 minus 1 1. Now, you see if I do the this matrix, whether it is full rank or not, if it is full rank, that means its determinant will be non-zero, and if it is rank deficient, that means its determinant will be 0. So, this matrix will not be invertible. So, you see by just doing the row operations, you can just add the first row and second row and replace it with the second row, then this row will be 0. That means 1 minus 1 will be 0 here, minus 1 1 will be 0 here. That means one row of the matrix will be 0. So, this is essentially a rank deficient matrix and rank will be 1. So, that means this has a physical significance too. So, that means our stiffness matrix for the stress, if I want to find out reduced row form, so 1 minus 1 0 0, I can write it like this. So, here you see that one row is essentially 0. So, that means this is a 2 cross 2 matrix. So, one variable is free variable, that means there are pivot variable is R is 1 and 1 is free variable. So, this matrix is not invertible. So, now if I find out an elemental stiffness matrix of a structure and then it is not invertible. So, how can I find out the deformation? If you know the stiffness form Ku equals to F that you are going to solve. So, K is your global stiffness matrix, U is your displacement that you want to solve, and F is the force vector. So, now if K matrix is not invertible, even this is true if you do connect with a multiple element, this rank will be deficient. That also we can say. For instance, if you write 2 truss element, 1 another 1, 2 truss element, 1 2 3. So, the final global stiffness matrix will look like this. So, 1 minus 1 0, then minus 1 2 minus 1, then 0 minus 1 1. So, this will be our global stiffness matrix. If you try and find out the rank of this matrix, you will see that rank is less than 3. So, this matrix will also not be invertible. So, this has a very physical significance because you see here if I rotate, if I have a truss element here, now if I do not put some constraint to the truss element, it can go anywhere. Suppose if I do not put any constraint to this truss element, it can go from here to here. So, there is no deformation in the truss element, it is just translation. Similarly, it goes from here to here and rotate it. So, there is no deformation. So, it is called rigid body translation and rigid body rotations. So, unless you restrict the one end of the truss or beam or the any structure, it will not have the deformation. So, this phenomena is actually reflected in the singularity of the stiffness matrix. So, now here when we derive this stiffness matrix, we have not essentially put this constraint here. So, what is this constraint? This constraint is the boundary condition. So, boundary condition means probably that end displacement is 0. So, this boundary condition when we incorporate into the stiffness matrix, then only it is non-invertible. So, that means then only its determinant will be non-zero, then only we can invert this matrix. So, then only we can find out the deformation of the other nodes or the position. But if we do not put the constraint, that means our matrix will be singular, and this singularity means that u, v, w or any deformations, rotations in case of a beam can have any value, and which is physically, suppose this is this, so it goes here and then rotate. So, anything, any translation, any rotation is possible. So, this phenomena is actually related with the rank of the stiffness matrix. So, when we encounter a rank deficient stiffness matrix, that means one of the reason may be we have not put the boundary condition correctly into the stiffness matrix. So, similarly in case of a beam, if we see, you know the beam stiffness matrix. So, this is a beam stiffness matrix that we know very clearly now. So, this stiffness matrix is also a singular stiffness matrix, because probably we will do it through the conjugate beam theory, where we will essentially put one beam and then we will make this thing delta amount slide. So, this will give me delta, and we will take unit delta and then calculate what are the moments here and here, what are the moments. So, all those things through this we find out the stiffness matrix. Now, here you see in this stiffness matrix, if I add these two rows, first row and second row, you will see and replace it again in the second row. So, that is 2 plus 1. If I do, then you will see this row will be essentially 0. So, that means it is again a rank deficient matrix. So, this matrix cannot be invertible. Similar case is obtained for a frame. So, in the frame, if you in case of a frame, we add axial stiffness also, because this A by L, A minus A by L and minus A by L, these quantities will be there. So, same argument if we do, and same row reduced echelon form or reduced row echelon form if we do, we can see that this matrix is also sorry, this matrix is also rank deficient matrix. So, as a whole, the idea is why we need to know the rank of a matrix here for the structural analysis case is that if there is a rank deficiency, if there is a rank deficiency, we cannot invert the matrix. So, here today we stop here. So, we will continue in the next module from the next week. Thank you.